Hello and welcome to this circuit example. This particular example demonstrates the basics of op amps in circuit analysis. This particular problem is problem 623 in Engineering Circuit Analysis by William H. Hott. And, well, let's get started. We can start this problem by redefining the basics of an op amp. We know that in an op amp, the current going through the op amp is equal to 0. So I sub OP is equal to 0. And that's the current from this branch to this branch. We also know that the voltage V sub N and V sub P have to be equal to each other because there's no change between this branch. So the nodal voltage right here is the nodal voltage right there. There is no difference. So we have V sub N is equal to V sub P, which is equal to also V sub A, which is our nodal voltage. Now we know that there's no current flow between these two terminals. Therefore, there is no current through this 1 mega ohm resistor, which we conclude then that there is no voltage across it and that the voltage through this branch of the circuit right here is equal to 0. Therefore, we know that all three of these nodal voltages are equal to 0, and so that'll help us out a lot. Now, as you can see, the sources are attached to the negative ends of the op amps. Therefore, we can conclude that these are inverting amplifiers. And what we want to do is we want to solve for V sub x located right here. In order to find that, we're going to have to find the positive voltage and the negative voltage across this resistor. And to do that, all we have to do is solve for the nodal voltages at A and the nodal voltages at B. However, we run into one problem with our nodal voltage at A because we have a current source here instead of a voltage source. So why don't we, using source transformation, convert that into a voltage source? As you can see, the problem is perfectly set up for that. So let's do that over in this corner right here. So we have our current is equal to 3 milliamps. And we know our resistance is equal to 1 kilo ohm. Now, using Ohm's law, we know that the resulting voltage of these two is equal to current times resistance, which will give us 3 volts. However, you can see our arrow is pointing away, and it might be easier for us to visualize it if we have it in the opposite direction. So why don't we invert our output and change the direction? So redrawing the circuit, we have something that looks like this. And this would be our negative 3 volts. This is our 1 kilo ohm resistor. This is our node A. And we also have a resistor down here and ground. What we really should do, and we can do this since all the components are in series, we can move this up here, and therefore we can figure out what our nodal voltage is going to be at A as a result of these components in series. And by the way, this is 21K. No, just 20. I think that was a mistake on my part. So that should be 20, 20, and the sum of them will be 21. So let's begin our nodal equation for A. So we have our node A, and for this we'll be using KCL, is equal to this equation. So our current in will be having a current in from this direction and a current in from this direction, since current flows from higher voltage to lower voltage. Therefore, we know, why don't we label this I1 and I2? So I1 plus I2 is equal to 0. And now this is where we can tell right away that it's an inverting amplifier, because if we rewrite this, we get I1 is equal to negative I2. Now let's break these up using Ohm's law. So we'll just find the voltages across each resistor, or well, sort of. We'll be finding the current. And so the current, looking at here, would be minus 3 volts minus our nodal voltage at A, which we already declared to be 0, over our cumulative resistance, which is 21 kilo ohms. And that is equal to negative the quantity and our greater voltage minus our lesser voltage. So V sub plus minus 0, which is again our nodal voltage at A, which we already discovered to be 0, over 100 kilo ohms. Now, I already did this on a calculator. You can solve it for yourself. You should get V plus is equal to 14.29 volts. Alrighty, so that's node A, and that was really all the trick there was to this problem. You can see node B is even easier because we don't even have a current source right here. So why don't we do that equation quick? So node B is equal to, now I'm just going to do this again, I1 minus I2. This will be I1 right here, and right here will be I2. And this should be our node B. I'm sorry, I made another mistake. Alrighty, so let's look at this. To our equation, 5 volts minus 0, which is our nodal voltage at B, over our resistance, R Thevenin, which is 10, is equal to negative the quantity of V sub minus minus 0 over our resistance, which is 100. Now, you can work this out for yourself, but you should get that V sub minus is equal to 50 volts. So now we have our positive side voltage and our negative side voltage. By the way, that should be negative 50. So now we sum it up. The voltage across V sub x is positive voltage minus the voltage at the negative terminal. And we already discovered these two quantities. So really it's just equal to 14.29 minus a negative 50, which is simply equal to 64.29 volts. And there you have it. That is the solution to the problem.